15.4.3, the adjusted R-squared value. One final thing to point out before moving on, it's quite common for people to report a slightly different measure of model performance known as adjusted R-squared. The motivation behind calculating the adjusted R-squared value is the observation that adding more predictors into the model will always cause the R-squared value to increase, or at least not decrease. The adjusted R-squared value introduces a slight change to the calculation as follows. For a regression model with k predictors fit to a dataset containing n observations, the adjusted R-squared equals 1 minus bracket the sum of squares residuals divided by the sum of squares total times n minus 1 in the numerator divided by n minus k minus 1, end bracket. So you can see they added another term based on n, the number of observations. This adjustment is an attempt to take the degrees of freedom into account. The big advantage of the adjusted R-squared value is that when you add more predictors to the model, the adjusted R-squared value will only increase if the new variables improve the model performance more than you'd expect by chance. The big disadvantage is that the adjusted R-squared value can't be interpreted in the elegant way that R-squared can. R-squared has a simple interpretation as the proportion of variance in the outcome variable that is explained by the regression model. To my knowledge, no equivalent interpretation exists for adjusted R-squared. An obvious question then is whether you should report R-squared or adjusted R-squared. This is probably a matter of personal preference. If you care more about interpretability, then R-squared is better. If you care more about correcting for bias, then adjusted R-squared is probably better. Speaking just for myself, I prefer R-squared. My feeling is that it's more important to be able to interpret your measure of model performance. Besides, as we'll see in section 15.5, if you're worried that the improvement in R-squared that you get by adding a predictor is just due to chance and not because it's a better model, well, we've got hypothesis tests for that. 15.5, hypothesis tests for regression models. So far we've talked about what a regression model is, how the coefficients of a regression model are estimated, and how we quantify the performance of the model. The last of these, incidentally, is basically our measure of effect size. The next thing we need to talk about is hypothesis tests. There are two different but related kinds of hypothesis tests that we need to talk about. Those in which we test whether the regression model as a whole is performing significantly better than a null model, and those in which we test whether a particular regression coefficient is significantly different from 0. At this point, you're probably groaning internally, thinking that I'm going to introduce a whole new collection of tests. You're probably sick of hypothesis tests by now and don't want to learn any new ones. Me too. I'm so sick of hypothesis tests that I'm going to shamelessly reuse the F test from chapter 14 and the T test from chapter 13. In fact, all I'm going to do in this section is show you how these tests are imported wholesale into the regression framework. 15.5.1, testing the model as a whole. Okay, suppose you've estimated your regression model. The first hypothesis test you might want to try is one in which the null hypothesis is that there is no relationship between the predictors and the outcome, and the alternative hypothesis is that the data are distributed in exactly the way that the regression model predicts. Formally, our null model corresponds to the fairly trivial regression model, in which we include 0 predictors and only include the intercept term beta 0. H0, y sub I equals beta 0 plus epsilon sub I. If our regression model has k predictors, the alternative model is described using the usual formula for a multiple regression model. H1, y sub I equals bracket the sum of beta k times x sub I k and bracket plus beta 0 plus epsilon sub I. How can we test these two hypotheses against each other? The trick is to understand that just like we did with ANOVA, it's possible to divide up the total variance, the sum of squares total, into the sum of the residual variance, sum of squares residual, and the regression model variance, sum of squares mod. I'll skip over the technicalities since we covered most of them in the ANOVA chapter, and just note that sum of squares mod equals sum of squares total minus sum of squares residual. And just like we did with the ANOVA, we can convert the sums of squares into mean squares by dividing by the degrees of freedom. Mean squares mod equals sum of squares mod divided by degrees of freedom mod. Mean squares residual equals sum of squared residual divided by the degrees of freedom residual. So how many degrees of freedom do we have? As you might expect, the degrees of freedom associated with the model is closely tied to the number of predictors that we've included. In fact, it turns out that degrees of freedom mod equals k. For the residuals, the total degrees of freedom is degrees of freedom residual equals n minus k minus 1. Now that we've got our mean square values, you're probably going to be entirely unsurprised, possibly even bored, to discover that we can calculate an F statistic like this. F equals the mean squares mod divided by the mean squares residual. And the degrees of freedom associated with this are k and n minus k minus 1. This F statistic has exactly the same interpretation as the one we introduced in Chapter 14. Large F values indicate that the null hypothesis is performing poorly in comparison to the alternative hypothesis. And since we already did some tedious, do it the long way calculations back then, I won't waste your time repeating them. In a moment, I'll show you how to do the test in R the easy way, but first, let's have a look at the tests for the individual regression coefficients. 15.5.2, Tests for individual coefficients. The F test that we've just introduced is useful for checking that the model as a whole is performing better than chance. This is important. If your regression model doesn't produce a significant result for the F test, then you probably don't have a very good regression model, or quite possibly you don't have very good data. However, while failing this test is a pretty strong indicator that the model has problems, passing the test, i.e. rejecting the null, doesn't imply that the model is good. Why is that, you might be wondering? The answer to that can be found by looking at the coefficients for the regression 2 model. Print regression.2. Call LM bracket formula equals dan.grump squiggly dan.sleep plus baby.sleep comma data equals parenthood end bracket. Coefficients. The intercept is 125.96. Dan sleep is negative 8.95 and baby sleep is 0.01. I can't help but notice that the estimated regression coefficient for the baby sleep variable is tiny, 0.01, relative to the value we get for Dan sleep, negative 8.95. Given that these variables are absolutely on the same scale, they're both measured in hours slept, I find this suspicious. In fact, I'm beginning to suspect that it's really only the amount of sleep that I get that matters in order to predict my grumpiness. Once again, we can reuse a hypothesis test that we discussed earlier, this time the t-test. The test that we're interested in has a null hypothesis that the true regression coefficient is 0, beta equals 0, which is to be tested against the alternative hypothesis that it isn't. Beta does not equal 0, that is, h0 beta equals 0, h1 beta does not equal 0. How can we test this?